Alrighty, good morning everybody. Welcome back to Galois Theory. How y'all doing today?
Hi, Lydia.
Hi, Lydia.
He's over there.
I'm just waving in that big direction because all you can see of me are my hands.
You should just
Okay. Plan for today. We're gonna talk some more about minimal polynomials and then talk about splitting fields. Getting very, very close now. Potentially by the end of this week we can start talking about Galois extensions.
Woohoo!
Whoa.
Might be Tuesday though. We'll see. Got my usual office hours today and tomorrow. Today at 1, tomorrow at 11 and at 1. The exam due Thursday. So, don't forget, take-home exam due Thursday. Okay, so homework 5. It's been passed back. I want to make a comment on it. If you claim something is a minimal polynomial for a particular element and in a particular extension, don't just give me the polynomial and expect that to be like a sufficient answer. At the very least, I want some explanation to why is that polynomial irreducible. Because just saying, yeah, it's easy to check that alpha maybe is a root of, like, for instance, alpha squared 2 plus squared 3 is a root of whatever polynomial. That doesn't necessarily make it irreducible. Meaning, just because alpha is the root of something doesn't mean that's the minimal polynomial necessarily. So for the exam, I'm going to be a little meaner about this. If you claim something's a minimal polynomial, at least explain why you know it's irreducible. And you can use like number 3 on this exam because, oh, I know the degree of the extension should be this, and it has the same degree as the minimal polynomial, therefore it has to be irreducible. Something like that. Yeah, you don't have to necessarily give me like a full
Recap of problem 3.
recap of problem 3, but make it clear why. Just saying, oh hey, I found a polynomial of which alpha is the root is not sufficient for saying this is the minimal polynomial over this particular extension.
I can definitely confirm I cited problem 3 at least twice.
Groovy. Any other questions or comments before we get started for today? So, mathematician one day decides he wants to get a side gig, earn some extra money, so he goes down to the local fire station, asks the fire chief for a job. Fire chief asks him a few questions, says, seem like a decent enough fellow, but before I give you an offer, I want to give you a test. So takes the mathematician out to the alleyway behind the firehouse, where in the alleyway finds a dumpster, a fire hydrant, and a hose lying there. Fire chief says, all right, suppose you came into this alleyway and you saw that the dumpster was on fire. What would you do? Mathematician thinks about it for a second and replies, well, I guess I would connect the hose to the fire hydrant, turn the water on, and use the hose to put out the fire. Fire chief said, that's a good answer, yeah. Now, follow-up question. What would you do if you came into the alleyway and you saw that the dumpster was not on fire? Mathematician has to think about that one for a minute. Before finally replied, well, I guess the first thing I would do is to light a match and set the dumpster on fire. Fire chief says, why would you do that? That's terrible. Why would you set a fire in the dumpster? Mathematician replies, oh, well, that way I've reduced the problem to one I've already solved. That's why you don't want mathematicians and firefighters. Alrighty, and with that, let's kick things off. So last time, we talked about how given some irreducible polynomial f of x over a field k, we can find an extension of k over which f of x is the minimal polynomial, assuming f of x is irreducible and monic, I should say. And the way we did that, to find an extension of k over which f of x is a minimal polynomial, is you take the field extension from taking the polynomials over k, modding out by ideal generated by f of x. We said since f of x was irreducible, this necessarily forms a field. It's a field extension of k because there's an isomorphic copy of k that's a subfield of this thing. And we said that f of x has to be the minimal polynomial in this field extension of this guy. X plus ideal generated by f of x. the coset, in other words, in this field that corresponds to just adding the indeterminate x. So that's one of the things we did. Prove that if you have something that's monic and irreducible, then it will be the minimal polynomial in some field extension. In the second half of class, we proved that this extension is unique in a way, meaning that if you have two fields that are isomorphic, k and k prime, f of x is irreducible in k, and you have one extension of k and another extension of k prime, where f of x or phi of f of x have roots, alpha and alpha prime respectively, then the simple extension k of alpha must be isomorphic to the simple extension k prime of alpha prime. And I think last time we had just gotten through the end of that proof when class let out. So just a quick recap of what we showed here is that if alpha and alpha prime, just kind of, because this is sort of a messy proof that says a lot of things, but really what it comes down to is if alpha and alpha prime have the same minimal polynomial, then their simple extensions will necessarily be isomorphic to each other. Any questions or comments about this result before we kind of look at a more simplified version as a corollary? Read over, read over. All right, so let's look at our corresponding corollary, which is really just a simplified version of this where k and k prime happen to be the same field. And what this says is we're going to let k be a field. F, an irreducible polynomial over k. Then we can say that if L and L prime are extensions of k, containing roots alpha and alpha prime of f, respectively, then there exists an isomorphism psi going from k of alpha to k. You know what? I'll even put the parentheses in just to make Parker happy. K of alpha to k of alpha prime, which fixes every element of k. Meaning psi of r equals r for all r an element of the base field. So essentially, this is saying the same thing as this theorem. It's just looking at the particular case where k and k prime are equal, and phi is just the identity function. Phi just maps every element to itself. And essentially says, hey, if you have some field and you extend it by two different roots of the same minimal polynomial, then the corresponding simple extensions you get will necessarily be isomorphic to each other. And it does it in a way, and this is going to be important. Oh, hi, Seamus. And it does it in a way where all the elements in K are fixed by that isomorphism, which is going to have an important role once we get to Galois properties in the next couple classes. Such a psi, by the way, we call a K isomorphism. One that fixes all the elements in K. Any questions or comments about this one?
So the only difference between this one and the corollary is that instead of a k and a k prime, you just have k and an L and an L prime?
Yeah. And the phi, yeah, you can think about this as being the case where k and k prime are the same,
Yeah.
and phi is just the map that maps everything in k to itself.
Yeah.
So, and in that case, that theorem just kind of has this nicer form. And I wanted to write out the nicer form because while that's a more general result, this is going to be the one that we're actually more often using, or in other words, we're using that more complicated theorem in this specific case most often. So, how about we look at a couple of examples? Johnny, you'll give us like
Yeah, so what would be the, what would be the, if we're using the other example, what would be the phi here? I just did, and then we.
Because if you think about here, our phi hat was the function that basically said, take some polynomial in k and then apply phi to each of the coefficients of that polynomial to give you a polynomial in k prime. You can think of phi, there's an underlying phi here that kind of fulfills the same role, but it's just the identity map. So phi hat, in other words, will be the identity map. As a function from k of x to k of x. Does that make sense?
Yeah.
Cool. Let's look at an example where we put this into practice. So let's look again at the case where k equals q, and we're doing k equals q quite a lot for a reason, because the complex numbers are nice to work over. And let's work with the minimal polynomial of m of x equals x to the fourth minus 4x squared plus 16. So, does anybody recognize an extension of k over which this thing is the minimal polynomial? So we've seen this polynomial a few times now. Anybody remember what we found was a root of this thing? Parker being a big a help as always. Try being a bigger help. Square root of 2 plus square root of 3. Come on, guys.
Oh yeah, that guy.
Actually, no. Now that I think about it, actually, no. Sorry, I was thinking of a different polynomial that's similar.
I know, I was just.
Okay, it's I plus square root of 3 is what I was thinking of.
Yeah, because I was like, there's
just
gotta be
testing
an
you.
I in there somewhere.
I was just testing
Yeah,
you.
you're right. Sorry, So here's one extension of Q over which this thing has a minimal polynomial. You can let 1L be the complex numbers, and let alpha just be I plus root 3. And so one of our simple extensions over here is we could say that our K of alpha is just going to be Q adjoined I plus root 3. So that's kind of using the old style approach where we just find some field for which Q is actually a subfield and say, hey, if we take this polynomial as a polynomial over the complex numbers, we know it has to split into linear factors. And one of the factors is x minus this bugger, alpha. So here is a extension over which alpha here has a minimal polynomial of m of x. That's kind of using what we've been doing for the past couple of weeks now. So if we do what we did last class, we could do something a little bit different. We can instead do a different extension and say, let's let L now this time be q adjoint x modded out by our polynomial here, m of x. And our alpha this time is just going to be x plus the side field. Here, what we're essentially doing in this case is our k of alpha prime is going to be essentially the whole field in this case, the whole q of x modded out by ideal generated by x to the fourth minus 4x squared plus 16. And we can think about this as being our simple extension of k. Technically, these are, like you could say that you can't adjoin q adjoin this, you can't take q adjoin this thing directly because it's two different types of rings. This is just a ring of numbers, this is a ring of cosets, they just weren't meant to be. But we could say that q, there's an isomorphic copy of q inside of here, and if we take q adjoined, that isomorphic copy of q adjoined this alpha, this is the corresponding simple extension that we would get. So some k of alpha prime, which is isomorphic to this thing, you could say. And so, what can we conclude then from our corollary, from our uniqueness theorem? Oh, the uniqueness theorem says if you extend by two roots of the same minimal polynomial, with the same minimal polynomial in two different simple extensions.
Well then, the second L prime and
Oh yeah, I forgot prime on that.
and q adjoined I plus square root 3 have to be homomorphic or isomorphic.
They have to be isomorphic.
Yeah.
Homomorphic is not a thing.
How?
I mean,
Any two things you can always form a homomorphism between, trivially, but.
yeah.
So in other words, just a second, let me Rose, I'll answer your question. We could say by the uniqueness theorem, uniqueness theorem being this guy, or its corollary this guy, should you so choose. This is an extension, you would join I plus square root of 3 must be isomorphic to this simple extension. Yes, Emily Rose, you have a question.
How is that L prime a simple extension?
Good question. How is this a simple extension? Usually when we think of simple extensions, when we originally defined simple extensions, we thought of them in the case of like, what if you just adjoin one element to your field? You had one element and nothing else. When the field extension is not just something, when your L is something that K isn't a subfield of, but K is isomorphic to a subfield of, you kind of have to alter your definition of what it means to take a simple extension. And doing something like this is kind of the isomorphic copy analog of doing a simple extension. Like we never actually like carefully define that, but this would be considered to be a simple extension of Q in this case.
Because it's isomorphic to.
Because it ends up being isomorphic to something that's a simple extension in the more traditional sense.
So you can either, basically it's one way you build it up from you have Q and then you extend Q.
Mm-hmm.
The other way, you go to QX, which has a lot more possibilities, and then you restrict it using the.
You restrict using, you mod out by the ideal generated by whatever you want your new minimal polynomial to be. And it turns out that's kind of two different ways of taking what we would think of as being a simple extension that produce isomorphic fields.
And you would get.
Even though these two things don't really look anything like each other.
But the bar elements would all just be the elements of Q adjoint I plus square root 3, right?
It's a little bit more complicated than that. Well, we'll explore that in just a second. Any other questions about how the uniqueness theorem applies here? So let's actually take a more careful look at this isomorphism and see if we can see, like, what are some of the elements here getting mapped to over here and vice versa. So, what do we know about this isomorphism? Well, from the uniqueness theorem, we know we have this phi that goes from one to the other. Typically, it's easier to start with this version and then go to the quotient thing. Because starting with the quotient thing, you then have to run into problems of how do you know your function's well defined. So, let's take psi as a function that goes from q adjoined I plus root 3 to polynomials in q, divided by, I'm just going to say ideal generated by m of x. We know it does it in a way where the alpha here, the root of q that we're extending q by, psi of alpha has to map to what element over here? What did we say? Alpha prime. Yeah. X plus ideal generated by m of x. What about psi of r for r an element in q? We say psi kind of maps every element in the base field to itself. Well, obviously r itself is not an element here because the elements here don't look like single numbers.
R plus the ideal generated by m of x?
Yeah, just take r plus ideal generated by m of x. But you can ask other questions too. Like what, for instance, would psi of I be? What, for instance, would be psi of root 3? You can show, by the way, that I and root 3 individually have to be elements in this extension. Kind of for similar reasons why square root of 2 and square root of 3 individually are elements of q adjoined square root of 2 plus square root of 3. So I is an element in here, in this thing. Let's call this our q of alpha, k of alpha. Square root of 3 is an element in k of alpha. How can we determine what psi of I actually maps to over there? It's not as simple a question. The question as it might originally appear. Elmore?
This, just a guess, but I have a feeling that it's just going to be the ideal generated by elements.
Why is that?
Because it's something in Q or K adjoined alpha.
Well, let me ask you this. Is I a multiple of m of x?
Not evident? I don't know.
If I was a multiple of m of x, then I would say maybe so, but I is not enough. I mean, you could ask, is there like anything you could, any polynomial you could multiply that by this to get I? And I would say no, because multiplying this by any non-zero polynomial can only increase the degree. It's never going to make it a constant.
Okay.
So say my favorite multiple of m of x is 0.
Okay,
So then it should be the minimal polynomial.
that sounds like nihilism to me, but go on.
Well, then what you should get, if you just kind of substitute 0 in for the ideal, you would just have the minimal polynomial of I. So it's probably the minimal polynomial of I plus m.
Oh, you're saying just
plus
evaluate.
the ideal.
You're saying literally evaluate this at I and then add that to the ideal. So what would that?
Yeah, you need I, not I plus square root of 3.
That would be like 1 plus 4 plus 16. So that would be like 21 plus ideal generated by m of x.
No, it should still be a polynomial. You need the minimal polynomial of I.
I was like,
Who says the minimal polynomial of I has to be an element over here,
it is.
or has an equivalent version of it? It is? Why is that, Lincoln? Because I'm not convinced.
X squared plus 1.
I mean, you could obviously take x squared plus 1 plus ideal generated by f of x. But unfortunately, nope. That's not quite going to work. I think we have to do a little bit of legwork involving this buffer, I plus root 3. I'm going to look at what happens if we take a linear combination of powers of I plus root 3. So let's see what happens if we have some a0 plus some a1 times I plus root 3 plus some a2 times I plus root 3 squared plus a3 times I plus root 3 to the 4th.
Why is your
Because I can count to 4, that's why.
Neither.
Shut up.
Just so we're good.
So what does this come out to? Bear with me here for a second. Well, we're going to get a0 plus, oh my gosh, I'm getting all choked up. a1, I'll say times the quantity I plus root 3. All right, what do we get when we square I plus root 3? Lincoln?
2 plus 2 root 3i.
2 plus 2, I'm going to write I root 3 just to spite you.
Okay. That's good motivation.
Spite is a great motivation. It's undervalued sometimes. Did you figure out what I plus root 3 cubed is yet?
Not yet.
Well, it's 2I plus.
No, not.
That feels very wrong.
What does? What did you get?
AI.
A constant term of 0? Or a real term of 0?
Yeah.
That's what I got too.
Whoa.
Oh. Oh.
And let's just combine this into various terms in a fun way. I'm going to get the terms that are just that don't have any square roots that are in Q together. Which, if we multiply all this out, the only two terms that end up being in Q, I think, are a0 plus 2a2. Let's take the terms that are a multiple of square root of 3, which would give us what? a1, just a1. Square root of 3 and no i's showing up, I should say. You can take the terms that have just an I with no square roots of 3, which will give us a1 again, plus 8a3. And then finally, if we take the I root 3 terms, we'll get what? 2a2? So I have a question. How can we write I? If this whole expression was equal to I, what can we say about a1 and a2 and a0 and a3? If all of this simplified to I, here we're going to do something. We're going to use the fact that 1 square root of 3 I and I square root of 3 are linearly independent from each other. There is no way to take a linear combination of any three of these things I've circled and get the fourth. So Lincoln, if this whole thing came out to just plain old vanilla I, what would be a system of equations we would get?
a0 plus 2a2 equals 0. a1 equals 0.
Oh, that sounds nice.
a1 plus 8a3 equals 1. And 2a2 equals 0. Here conveniently everything's 0 except a3, which is 1.
Oh hey, that sounds nice. Because from this, I think we can immediately say, A naught has to be 0 because A naught plus 0 equals 0. Well, line 2 literally says A1 equals 0. Last line says A2 equals 0. Isabel, what do we get for A3?
1A.
Yeah, we get 8A3 equals 1, so A3 equals 1/8. So what does that tell us? Well, it tells us that if we go back to this equation, that tells us that I is equal to 0 plus 0 times I plus root 3 plus 0 times I plus root 3 squared plus 1/8 times I plus root 3 cubed.
Okay, I might just be straight lost, but why are we only going out to A3 and not going further to like A4? I mean,
Good question. I'm gonna answer that in just a minute here. Here's what I is. So what's psi of I?
1/8 times x to the third plus the ideal.
That's how you can solve this. Yeah. We don't really know much about what things get mapped to in this ring over here. But we do know what alpha gets mapped to. We do know what I plus root 3 gets mapped to. Which means we know what any linear combination of what any polynomial of I plus root 3 gets mapped to. Any polynomial of I plus root 3 is going to get mapped to, well, that polynomial in terms of x. So the fact that I satisfies this polynomial in terms of alpha means that psi of I has to map to that same polynomial plus the ideal, where you've replaced alpha with the variable x, coming from this fact that alpha gets mapped to x plus this ideal. And this also relies heavily on the fact that we need psi to be a homomorphism. If psi was not a homomorphism, knowing this would not help us determine that. Matthew, you had an interesting question. Why did I only go out to A3 here, to I plus root 3 cubed? Why didn't we go out to an A4 term, or an A5 term, or an A6 term?
Basically, the I plus root 3 to the fourth is going to be linearly dependent on the earlier smaller powers.
Yeah. It's because once we get up to I plus root 3 to the fourth, I plus root 3 is actually going to be remember, I plus root 3 is a root of a degree 4 polynomial over Q. So if we had more than A3 here, if we had like a plus A4 I plus root 3 to the fourth, for instance, we'd have a linear dependence relationship between all the a's of k's, which means we wouldn't be able to get a unique solution like this. It would end up being redundant in that case. And in general, you only need to go up to 1 less than the degree of whatever the minimal polynomial was originally. Does that sound good, Matthew?
So basically, it's just we're trying to find like
We're trying to set this equal to I, and we're solving for A naught, A1, A2, and A3.
is it kind of like finding like I guess the minimal polynomial, but like instead you're just basing it around I?
Sure.
Instead of 0?
Mhm.
Okay.
Eleanor?
Why does root 3 come out to x minus 5?
To X mine? Wait, what? You've already done this one?
Yeah.
Hold your horses. We're still doing the I
Oh.
example.
I was about to say that.
Okay.
Well, I was about to say the same thing.
Okay.
Well, like a psi of square root of 3.
Does anybody have any more questions about the calculation for I before we move on to square root of 3? Oh, Andrew, I thought you were going to ask. Dr. Gerstle, we got AI here. that this cube is 8i? Couldn't we have just divided both sides by 8 at this point and been done? And the answer is yes, we could have. But I wanted to have this formula so that we could plug in other values as well. So what is psi of root 3, for instance?
Is it psi of root 3 is equal to x minus 1 over 8x cubed plus the ideal generated by f(x)?
How did you get that?
I got that, well, first of all, we know that a1, if you make that equal to 1, you just get I plus square root of 3, but we already know what I is, it's 1/8 of x cubed. So if you take the linear combination that sort of removes that I from the I plus square root of 3, you're just left with square root of 3.
I see.
I did it,
How did you do it differently?
very good.
There's a couple ways we could do this.
Well, yeah, I guess I sort of did that, I just did it in a later stage. So I went down to that last line and said A1 equals 1, everything else equals 0. Or everything else has to, the multiples, or the,
Yeah, so we
and
get,
you get out to the same thing.
let's do the same approach. If we were setting all of this bottom line equal to square root of 3 instead of I, what would we'd get a naught plus 2a2 equals 0. A1 equals 1. 0 equals A1 plus 8A3. And I root 3, that's 0 equals 2A2. So then if we solve for all of our variables, we get A9 equals, and that's scary, A1 equals 1. A2 equals 0 from this bottom line here. So the top line tells us A naught plus 0 equals 0. So A naught is 0. What's A3 here? Yeah, because we get 1 plus 8A3 equals 0, 8A3 equals -1, solve for A3, you get -1. So from this, we can say that square root of 3 is, going back to this top line, 1 times 1 for A1, we get 1 times I plus root 3. So alpha, in other words, minus
1/8 alpha cubed.
1/8 alpha cubed,
Which is what we got first.
which means psi of square root 3 is going to be x minus 1/8 x cubed plus ideal generated by m of x.
Oh.
Does this have to be a minimal polynomial, or is it just like we're just trying to find the
What?
like, because I feel like you can factor out.
I'm sorry, Matthew, I can't hear anything over this cackling right in front of you here. Start over. Does what have to be a minimal
Does
polynomial?
this have to be like irreducible, or
No.
Okay, because I was just like you.
No, this polynomial in terms of alpha doesn't have to be irreducible. This is not the minimal polynomial of anything. This is just how can we write something in this ring, K of alpha, as a linear combination of powers of alpha. And writing something in this ring as a linear combination of powers of alpha then helps us to determine where is psi going to necessarily map that element.
So we're just trying to find the mapping basically.
We're just trying to, I'm just interested in seeing where does this map actually maps a few elements. You can kind of get a sense for how it works.
I found another way of doing it.
Oh, did you? Did you
Yeah.
find a shorter and easier way?
Yes.
Does it involve knowing this one?
Yes.
Okay,
Um,
do tell.
so we know that alpha is I plus root 3. So alpha minus I is going to equal root 3. Which then we already know what I is. And psi of alpha is just x plus the ideal generated by m of x. So you just get x
Yeah, I
minus
was gonna say.
That's what I did.
I was gonna say that, yeah.
That
I was
makes
curious.
a lot more sense.
I was curious if anyone was gonna see that. You could also do it this way too,
Uh,
which would give us x minus 1/8 x cubed plus this ideal, and you could skip having to solve a system of linear equations and get the same result in the end. How about that?
That's kind of crazy.
Indeed it is. And if we wanted to, we could also look at psi of other various values. Like we could take psi of 5i minus 6 root 3, for instance. And from this point, you could either go through this whole process again, solve a system of equations, or you could take 5 psi of I minus 6 psi of root 3, see what that comes out to.
I squared is equal to half x squared.
Huh?
Even 1/2 x squared is equal to I squared.
Neato burrito.
So is the M of x, is that just basically the kernel of this?
M of x was the original minimal polynomial. And so you can think about the ideal generated by M of x in this ring as being as corresponding to the 0 element in our L prime.
Oh, that makes sense.
So yeah, in other words, it's not really the current. Well, the current. It's the current. Well,
Yeah.
Yeah, it is.
Isn't it like the null space, like?
Because
where
it's
it's
gonna
at
map
that
to
space?
0.
alpha plus 1 minus 1/8 alpha cubed would be in the kernel. Because this is not an element of k of alpha, so it's not eligible to be in the kernel. But if you replace your x's with alphas, then yes, this Matthew would be in the kernel of this isomorphism side.
Like, isn't everything in terms of alpha? At least in K.
No, because alpha doesn't map to 0 element. Alpha, remember, maps to x plus the ideal, not 0 plus the ideal.
Okay.
This is not the 0 element of that ring. The kernel of psi would correspond to elements over here that map to the 0 element here, meaning this thing, which would correspond to things like alpha minus 1/8 alpha cubed.
So I just remember in differential equations, you'd have like the general equation, basically, where you'd always have to have that and there's like a particular equation. Is that kind of like the same thing here? Where like.
Yep.
Okay.
Yeah, it all comes down to the fact that these values are linearly independent, meaning you could come up with like a generalized solution. It ends up being like powers of this, I think, or something.
Okay.
But yeah, you could certainly do that. Yeah, good call. Let's do another example. Different fields, different polynomials. Everyone okay if I erase this stuff? Let's look at f of x equals x squared plus x plus 1. Oh, enter K. Let's have some fun.
Oh, my science. Oh.
Oh, that's weird. Over there now, so
That's kind of crazy.
Yeah, who says we have to work? Who says our base field has to be Q? Our theorems and such are applying to arbitrary fields, so that's a field. We can consider this to be a polynomial over that field. So how do we know that f of x is irreducible over z mod 2?
It looked that way.
It looked that way.
We can test it.
But we
Alright, how do we test it?
Put in 0 and
Wait, can we just?
I plugged in 0, I got 1. I plugged in 1, I got 1.
those are not 0.
Oh, those aren't roots. This thing has no roots and it's quadratic, therefore
It's
irreducible.
irreducible.
Yeah. So we can immediately say f of x is irreducible over k because it's quadratic and has no roots. Why? Because f of 0 equals f of 1 equals 1 in this case. So we know it's irreducible, so we can do our whatchdoodle. So now, we'll be ready for this, Parker.
I'm so ready.
Let's take polynomials over z mod 2,
I'm not ready.
modded out by ideal generated by x squared plus x plus 1.
You're like taking everything that I hate and just like smushing it all together.
Essentially, we're just doing the same thing we did over here.
Yeah, but now it's even worse.
All I did was I replaced q with z mod 2.
Oh.
Oh no, our base field has. Oh no, our base field technically is made up of cosets, and we're taking a quotient of that thing. It's quotients of quotients.
It's all gobbledygook.
It's all gobbledygook. So how many elements does this ring even have? Turns out the answer is it's not that many.
Fewer than
It is fewer than
2 or 4.
it's fewer than 8.
It's 4.
How do you get 4?
Well, if we let alpha be a root, then 1 and alpha is a basis. Like you're just like all higher up.
It feels intuitively obvious, but it's hard to put into exact words. Yeah. Here's the catch. We know that anything that's a multiple of x squared plus x plus 1 is going to be in this ideal, and thus is going to get mapped to 0. So here's our elements. 0 plus ideal generated by, let's say half of x, because I'm too lazy to write all that out. You got 1 plus ideal generated by f of x. We have 2 plus ideal generated by f of x. Oh wait, we already have that one.
Times 2.
Because 0 and 2 are the same in this ring.
Wait, we also have
X!
I was about to say.
And one more.
Oh, wait, it's 1 x squared.
X squared?
X plus 1.
What about 1 plus x?
Oh, wait, but this x squared.
Technically x squared will work, but I like this way better.
Oh. That'll do it.
Here's our 4 elements.
How do we know that x squared is the same?
But Dr. Gerstel, what about x squared?
Dr. Gershwin, what about x squared?
Well, I would say this. X squared equals x squared plus x plus 1 minus. Would you agree with that?
I would.
Yeah.
Yes.
Everything that's of this form we're saying is equivalent to 0
Oh.
because that's in the ideal we're modding out by.
Oh.
So really we get the same thing as negative x plus 1.
But that's the same thing as.
That's the same as the positive because in z mod 2 positive and negative is 1 equals negative 1.
That's kind of crazy.
And so x squared plus this ideal ends up giving us the same thing as just 1 plus x plus this ideal.
And it's kind of nicer to express things as linear combinations of things that we already have.
Well, it's just that, like, I don't know, 0, 1, x, 1 plus x, these are nice linear terms. X squared is quadratic, that's scary.
We don't want.
But here's the thing, the fact that x squared plus x plus 1 is a degree 2 polynomial, the fact that we're modding out by a degree 2 polynomial means that all of the elements of this field should have coset representatives that could correspond to something that's of degree 1 or smaller. If this is a degree 3 polynomial we modded out by irreducible, we have 0, 1, x, 1 plus x, x squared plus 1, x squared plus x plus x plus 1, and those would be the unique coset representatives. Because then x cubed we could write as a linear combination of other things, like what we did here. If this had been x cubed plus other stuff.
Would it make calculations easier if we use x squared?
I don't know, maybe.
I know.
So we can even put like a Cayley table together for this if you wanted to. I'm not going to because that sounds tedious, but let's do a quick calculation. Let's say we take 1 plus x plus the ideal, and let's say we multiply this by, I don't know, x plus the ideal. Well, by definition, we multiplied 1 plus x and x together to get x plus x squared plus the ideal. But which one of these four buggers is x plus x squared plus ideal equivalent to in this ring? Oh, 1? Why is that?
Because x squared is x plus 1, so you get 1 plus x, which is 1.
Yeah. This is the same as taking f of x plus 1 plus ideal generated by f of x. And adding f of x is the same as adding 0 in this quotient ring. So this comes out to the same thing. It's just. But Dr. Gerst, shouldn't this be f of x minus 1? But minus 1 and plus 1 are equal in z mod 2, so.
What were you looking at? You were.
Looking at what?
What was the original?
To go from here to here?
No. What was the goal of that?
Oh, just to say, hey, if we multiply this and this, which one of these four cosets do we
okay.
get? Just give you all a bit of a reminder of how to work with coset multiplication.
F of x more like j of x.
Shoot. Oh.
But it isn't.
Yeah, it is. It is in my notes too, and I realized that as I was writing this all out on the board, and like, whatever, it's f of x now.
It is a minimal polynomial, so we could just use that over and over again,
Well, what's a minimal polynomial?
right? That's
This
it's the
thing?
minimal polynomial.
It's the minimal polynomial of this guy,
Yeah.
x plus ideal. Yep, that's what we proved. That's what we proved as part of the that result. Questions, comments, concerns? I bring up these examples because A, I think they're fun to play around with, and B, I want to make sure you all understand like what are these extensions that we're getting? Like how do these computations actually work? Because we're going to be doing more of them in class and on the homework. And I'll probably give you something like this on the final too. All right, y'all ready to talk about splitting fields? So, what's a splitting field? So, we've talked about if f of x is irreducible, how can we find an extension of k over which f of x is the minimal polynomial of something, or has a root of something? We're going to go one step further in the next packet. Instead of just asking, how can we find an extension of k over which f of x has a root? We're going to ask the question, how can we find an extension of k over which f of x breaks down into linear factors? So if f of x is degree n, how can we find an extension of k over which f of x has n roots? And that's going to be the idea of taking a split field. Here's the next packet. What panel? What panel? And toss that out in the hall. Oh, wait, Bart.
Hi.
You want one?
Yeah.
Why did you say so?
Because you give them out to everybody.
Clearly I don't. I didn't get one to you.
Yeah, I don't know. I feel insulted. I feel slighted.
So, let's talk about splitting fields. Because this is going to be ultimately how we define our del law correspondence, is going to be on these things. So, the idea of a splitting field is we're going to have k field. F of x, some polynomial over k. And we're going to say that L is a splitting field for k.
You have 4f over k. Is there a difference?
It's a splitting field for f over k. You're right. I should say for f of x. If two things happen. One, f of x can be written as a product of linear factors in L of x. And saying that f of x can be written as a product of linear terms, our shorthand for that is saying f of x splits over L. Or splits completely over L. Splits here just means breaks up into linear terms, splits into linear terms. Here, min. Second condition for our splitting field is it has to basically be the minimal field extension, the smallest field extension for which this happens. In other words, f of x doesn't split completely. Over any subfield E with K a proper subset of E, a proper subset of L. What's lame?
Why can't we have more of them? And I could just say C for everything over.
You could not because if K is C mod 2, that is not a subfield of C.
Okay, but
In the case of Q, yes, you're right. The case of why do we need the second condition is A, because I like spiting Lincoln and making his life more difficult, and B, we're going to have a theorem that basically says splitting fields are unique up to isomorphism, which if we didn't have the second condition would be very much untrue. Let's look at a couple. Otherwise, you're right. You just take any algebraic closure and say that's your splitting field and call it a day. Alright, let's let k be equal to q. F of x is going to be x squared plus 1. By the way, f of x doesn't have to be irreducible to find a splitting field. F of x could be reducible, in which case finding the splitting field just becomes easier. So, I want to find an extension of q, a minimal extension of q, over which this can be written as a product of linear terms. And, yeah, I already said the word minimal. Janice?
I think the minimal extension is going to be the q adjoined I root 5.
Why do you say that?
Because I don't know how you would break this thing up into factors without having I root 5 in there, but I don't think you need it.
Well, in C, the complex numbers, we know we can break this up into linear terms as x minus I root 5 times x plus I root 5. And so in order to get roots of f of x, in order for f of x to split into linear terms, we need an extension of q containing I root 5 and negative I root 5. And so what's our smallest extension of q containing both I root 5 and negative I root 5?
Q adjoin I root 5?
Don't we need to also adjoin negative I root 5?
That's also an element though, by subtraction, or closure over subtraction, right?
Technically we do, but you're right, but if we add in I root 5, we get negative I root 5 for free.
It doesn't hurt if you add.
But it wouldn't be the smallest, or would it be? I
It
guess
wouldn't
it would be the
it's the
same
same.
thing.
It wouldn't do anything.
Did it make you have to write more?
No.
Right, or
These are
no.
the same, and so they're the same field, so both answers were, the first answer is just more succinct. But both of these could be considered the splitting field of, a splitting field of f of x over q. Start with the rationals. All that we have to include is I root 5, and since I root 5, adjoining I root 5 will automatically adjoin all rational multiples of I root 5, such as negative 1 times I root 5. Adjoining I root 5 will give us its negative for free.
And since the degree of that extension is 2, we know that it satisfies the second property because it's prime.
Well, I mean, couple ways. We know We know Q itself is not a splitting field for this thing, because this thing does not split into, clearly does not split into linear factors over Q. So that means the degree of the extension has to be at least 2. And this is the smallest degree that it could possibly have then, because I/5 satisfies degree 2 polynomial, like, I don't know, x squared plus 5. So that would be one way to do it. The other way would be to say, by this, we know I/5 has to be included in our extension. If I/5 has to be included in the extension, then this has to be a subfield of your extension. Well, what's the smallest thing including that? It's that, Q adjoint I/5. A couple ways you can make the argument for why that satisfies the minimality condition. But you're right, you could appeal to the degree of the extension as well. All right, how about this one?
Is that deliberately not what you have in the?
That's deliberately not what I have in the packet to spite you. We'll do that next one in the packet in a second. But I thought of this one this morning and I said, oh, I have to ask this. So, what do we have to adjoin for Q in order to get a field extension where this splits into linear terms?
Nothing.
Nothing, so what's our splitting field?
Q.
Oh, hey. That one's easy.
Wait. Wait.
Where is it?
But Z is. Because Z works.
Is Z a field extension of
No,
Q?
but Z with.
Is Z a field?
But
But Z with what?
I don't know.
You gotta have an actual extension of Q in order to be a splitting field.
Can you take things out of Q? Take out everything.
No, because then it wouldn't be an extension of K. Actually, I guess technically it could be, because you would have infinite fields being isomorphic to subfields of proper subfields of these subs. But no, don't do that. That's bad. Technically you can, but that way leads to madness.
Question.
She's already met.
Yes.
Do we need the not equal in condition 2 in the first one? In the definition of a splitting fields.
Yeah.
The second word, like the bottom.
Yep.
Should that be just like K subset equals E subset not equals L?
Sure. Yeah. No, K can certainly be equal to, yeah. Yeah, this would be a case where E could certainly be equal to K if your polynomial already splits into linear terms. Yeah, E could certainly be equal to K.
But
It
they're
just,
equivalent statements, right?
well, it doesn't split over any subfield with that. No,
Yeah, that's
actually,
it, yeah,
actually no, we need this, because K was, if we said K, E couldn't equal K,
Then K wouldn't be.
then
K.
Q wouldn't work for itself.
Oh yeah, that's the
Because-
reason, because
Then there's no E does not equal L.
Let's see, does f of x not satisfy over any subfield E that's bigger, oh. Okay, fine.
Okay.
Technically, you're right, I think, I'd stop and look at this again. Don't make me put that line back in again, please. Moral of the story is, if it splits into linear terms already over K, then your splitting field can just be this.
Back to L's.
Gosh darn it.
Oh, yeah, because then you get L equals K.
look,
And then-
still right.
Andrew, you're not supposed to do this to me. It's supposed to be Lincoln's one who does this sort of thing to me. Okay, let's start from the top. L is a splitting field for f of x over k if blah, so k could certainly do that if, in this example, f of x doesn't split completely over any subfield E.
Okay,
Or
okay.
any sub.
But look,
So in this case, it's vacuously true.
It's vacuously true.
yes, I guess it works.
Yes, it works.
Either way, it's vacuously true.
Yeah.
Stop doing this to me. Oh gosh, this is where having this be my third consecutive class starts to get to me, and I start doubting myself.
It's the best kind of true.
Because
All right, let's do another non-trivial example.
also works. Because it's still vacuously true.
Yeah.
What the heck?
What was that?
I'm a duck in my class? Alright,
That was definitely chicken.
x to the fourth minus 2. Hey, we need root 2.
We also need.
Well, we need more than that.
Yeah.
Root 2 is,
We need some
no, root 2 is not a root of this thing.
We need
Oh, because that's
fourth
the
root of 2.
I didn't take x squared minus 2, silly.
We need a 0.
Yeah, we're gonna need fourth root of 2.
And eyes.
And we're gonna need eyes. Yeah, we
Times
wanna
the
be able to
fourth root of
see,
2.
yeah, we wanna be able to see what's going on here. I don't know what.
Why do we need that?
Because you were gonna x squared minus root 2 times
You have
x
to
squared
split the
plus
other
root
one.
Why is this? No.
You have to
Why
have
wasn't
four
it just x squared?
Because it wouldn't be as
Because it would be as ridiculous.
These two terms multiply to x squared minus root 2.
And then plus root 2, you get the I as both.
X minus I fourth root of 2. X plus I fourth root of 2. So what do we need? We need plus or minus fourth root of 2, and we need an extension where we have plus or minus I fourth root of 2.
You can handle it.
Shut up. So what would be a minimal extension of Q for which we get plus or minus fourth root of 2 and plus or minus I fourth root of 2? Matthew?
Would it be Q and then you just get one of the four, or fourth root of 2 and then one of the I fourth root of 2 and then you just pray that the negatives work out?
Well, the negatives worked out. Well, let me ask you this, Matthew. Is negative 1 a rational number?
Yes.
So negative 1 is an element of Q, hence negative 1 is an element of this thing.
Yeah.
And since this thing's closed under multiplication, if fourth root of 2 is in here and negative 1 is in here, then negative 1 times fourth root of 2 has to be in here, hence negative fourth root of 2 is in there.
Prayers work, yeah.
I do.
Your prick,
I do want to.
miracles do happen sometimes.
I kind of do want to
So
see a
I-
proof by prayer though. It'd be kind of fun.
I've never done one of those.
Proof by prayer.
That sounds like Raman. That's like a Ramanujan type proof. That's how he would. That's basically what he would do.
There'll be lots of mini Greek philosophers we can go
Eh.
if you start doing church stuff.
Bring them on. All right, here's a question. What's the degree of this extension over Q? Eleanor?
It's 4.
It's 4. Yay!
Because I like 4.
Too bad it's not 4.
Why is it not 4? Because the degree of the g of x is 4.
Oh no, g of x is 4, but I didn't say the degree of the g of x has to match the degree of the
Right.
splitting field extension. Oh no. All right,
What if
Oh, no. It's just,
I'll give you a hint.
Is it?
It's
Is it?
just
is
This
it-
thing,
yeah.
this thing is a degree 4 extension over Q.
Excuse me? Why?
Because this thing
Oh,
fourth root of 2 has a
right.
minimal polynomial x to the fourth minus 2.
Right.
So
Oh, so it's
since this is a subfield of this thing should have a bigger degree extension over Q than this does.
I feel like
For
it
no
should be 8
particular
then.
reason. Well, it's not that hard.
It should
I
be
kind of like to see a proof of that.
8.
Well, just do the.
Alright,
No, it's
this thing, would you agree that fourth root of 2 is a root of this polynomial?
Six.
If fourth root, then square root of 2, and then 3/4.
I've claimed this is irreducible. Why? Eisenstein, p equals 2, boom.
Oh.
Is it 6?
No, I think it's 8.
No, I think it's 8.
Because you have 4 from the 4 root 2 and then 2 more from the
Because you can have I or not.
multiply the 2 and
Yeah, it's gonna be 2.
You have to multiply them though, right?
yeah, so it's 2 times 4.
Yeah.
Which is
But what's 2 times 4?
8.
Oh, it's like this, yeah. It's beyond 4.
Oh, hey, that's it.
Yeah, see, this is what I was talking about.
Now we just have to prove that 2 times 4 is 8.
But is it really?
I don't know about that.
Is everyone okay with the fact that this term is 4?
Yes.
Yeah.
Is everyone okay with the fact that this term is not 1.5? Sorry, Jonah, it doesn't come out to 6.
Okay.
So, adjoining I fourth root of 2 to Q adjoint fourth root of 2. Why?
Because as basis, you can just take like 1 and I.
That's probably a nicer way to write that makes it a little bit more clear.
Yeah.
The reason being, before Matthew asks me, is if if clearly this should be a subset of this, because if 4th root of 2 and I are in the field extension, then their product, I 4th root of 2, should be in the extension. And similarly, if 4th root of 2 and I 4th root of 2 are in the extension, then you should be able to take I 4th root of 2 divided by 4th root of 2 and get something still in the extension, namely I. So these are the same extension.
So why do we write it the other way?
Because that's what someone told me to, that's what Matthew told me to do, is to write it this way first. Sorry, Matthew, gotta be honest. So degree of this extension, 2. It was 8. Sorry, Eleanor, it wasn't 4 either. And I have no idea where Jonah got 6 from, but turns out it's an extension of degree 8. So here's a thought to end class on. What can we say in general about the degree of the splitting field as an extension? Well, it turns out we can always say this. It's not just going to be equal to n, Eleanor, or the degree of your f of x,
Quite greater than that.
but it's going to be less than or equal to the degree of f of x factorial.
Excuse me?
No, it makes sense, because it's a, when you do
Combinatorial.
the expansion,
Will
it's
it
combinatorial.
Oh, yeah, that makes sense.
The
I don't like
Yes,
Degree of f of
We
x.
proved that.
and that'll be, and that'll come out as a consequence of our proof of this fact between next time.
Yeah. Yeah, but it just become bigger. It's just a bigger number.
So for instance, 8 here, what's 4 factorial? 24. 8's less than or equal to 24.
Oh, yeah, it's like pi.
So in fact, the degree of your polynomial, that degree factorial will always give you an upper bound on how big the degree of the extension field can be. And we'll write a formal proof of that next time.
It's also always divided by
Pi squared over 6
Yes.
is
Am I,
Yes.
am I in, I am having deja vu right now, yes. It will.
Yeah.
So that's just the gamma.
This actually isn't too hard to prove, just do, basically just apply that theorem up there
Probability
and
of being done.
you do induction.
Probability of being done.
This is essentially how you
One
prove
is-
it.
series that converges to
Basically, it's not.
Hey, Parker,
Pretty number.
in the video. Oh, Lydia, hope you're having a good one.
I need you to stare at the camera before.
Oh, I'll stare at the camera.